What's that? Ampere's law is how we relate the current with the magnetic field, so that the differential form of the Ampere's law is that the curl of the magnetic field can be equated with the mu 0 times J, where J is the current density in a space. And the integrated form of this is taking a line integration of the magnetic field along the line we take is the one you can equate with the current going through the surface which is enclosed by the closed loop whose integration is taken like this. Okay? So this is the Ampere's law, what we have. And you can compare this. So this was to find the magnetic field when there is a current density in space. And if you compare the Ampere's law with the Gauss's law, which is for the case of the electric field, can be given in parallel. That so once you have a Coulomb's law, which is the electric field is inverse square disproportional from the point charge, and if you take an integration of the charge density in a space, then you can have the electric field in a space. And once you have that Coulomb's law, then we can derive the Gauss's law. And we usually use the Gauss's law to find the electric field when there is a symmetric charge distribution in a space. And the form of the Coulomb's law was given in this way, that 1 over 4 pi epsilon 0, and take an integration of charge density distribution in a prime coordinate, and a gamma, which is gamma square, which is the distance between the r prime and the position vector r, where we want to have an electric field in that position, and take the volume integration, which is a Coulomb's law. And once we have a Coulomb's law, we can have a Gauss's law, which is also, in the case of the differential form, is given as divergence of electric field is correspond to the charge density divided by epsilon 0 for the case of the free space. So here, law is the law enclosed by the Gaussian surface divided by epsilon 0 for the case of the free space. And in the same way, we can derive the magnetic field that from the Biot-Savart's law. And once we have the Biot-Savart's law, we can have the Ampere's law. Okay? In a way that the magnetic field at a position R is correspond to mu 0 divided by 4 pi, and taking integration of current density in a prime coordinate, and divide by the distance square, distance between r prime position and r, and you take a volume integration. If you have in this form, okay, and then you can have the Ampere's law in this case in a form that the curl of the magnetic field is given by mu 0 and j at the position r like that. Okay. So if you see in parallel, you still can see the difference between the electric field and magnetic field in this case. Is that so what electric field proportional to the law is the electric field the divergence of electric field, and what you can equate with the mu times current density is a curl of the magnetic field in this case. This is the divergence and this is the curl. Okay, so this which is bit of differences between the electric field and magnetic field in each expression. Okay? So once we have the Ampere's law like this, and we use Ampere's law to find the magnetic field when there is a symmetric distribution of the current density in a space. As like we use the Gauss's law normally to find the electric field when there is a charge distribution which is distributed in a symmetrical way. We can practice how to apply the Ampere's law in a normal situation by seeing the couple of examples. So number 5.7 is about the current in the wire. Okay, let's say there is a current I is flowing in the wire like this, and the question we want to ask is what is the electric field, magnetic field around the wire, the distance s from the where the wire located. Okay, and we actually get the answer for this by getting the magnetic field through the Beer-Savart law. In this case, we can actually find the magnetic field around the current in the wire using the Ampere's law in this case, because this is a very symmetric in a way that the current is in a straight line flowing from the minus infinity to the point of infinity. Okay? For that, we can use either differential form or integrated form of the Ampere's law, in a way that if we apply the integrated form, will be this times mu 0 I enclosed. Okay? And for the case, if you take the integration around the loop that we have been taken here, so using the right-handed rule, that the magnetic field, strength of the magnetic field along the circle whose distance, whose radius is given by s, centered at the wire, is a constant B field, because it is this equidistance from the current. So that what you can do is a magnetic field will be constant over the integration. And if you take the loop integration along the line around the circle, and it corresponds to the length of the prefold distance, which will be 2 pi s, will be the evaluation of the left-hand side, right? And for the case of right-hand side, we have a mu 0, and the amount of the current flowing the plane across the plane, perpendicular to the plane, will be just simply I, such that we will have strength of the magnetic field in this case, like at the position position distance s from the wire will be mu 0 times I times divided by 2 pi s. Okay? This is a magnetic field that we can have. And this is the same result that we have from the application of the Biot-Savart's law, if you remember the example in the previous class. Okay? And so this is a similar way to apply the Gauss's law, but the difference in this case is we actually take the line integration rather than volume integration for the case of the Gauss's surface. Okay? And we can further see the application of the Ampere's law in the example 5.8, like this, for the case of surface current. For the case of a line integration, no, the infinite plane. Okay, so that, like, let's say there is an infinite plane like this, and the current is flowing with the line density, surface current density given by K like this. Then let's say, the coordinate is given in a Cartesian coordinate like Z, and let's say the current is flowing in the X direction, and it's given in the Y direction like this. Okay? And the question is, what is a magnetic field above that infinite plane is the question. And here we can actually find it using the Ampere's law again. Line integration of the magnetic field will be mu 0 and current enclosed like this. And to apply this, we should take a proper Ampere's loop in this case. And the Ampere's loop that we can take can be the plane perpendicular to the surface current, in a way that we can, if we take a loop like this, line like this, just above the surface, you can take a line like this, and then go inside of it. You can close a loop by taking this rectangular loop, rectangular shape of the loop like this. And then, if you think about the right-handed rule of the relation between the magnetic field and current, you may say that if your thumb is pointing the direction of current, and the loop will be in a anti-clockwise way, and the magnetic field in this shape. And what we can say about this is that since if you look at the current in the plane of the loop which have been taken, so in the loop given by the yellow line like this, okay, this is a line. And then here we have a sheet of the a plane where the current is flowing, let's say, going this direction. So we can denote with this direction. So these will be the surface current coming out from the blackboard, you say. Then you can say the effect of the magnetic field from this current density, like this, will be uniform along the line of the surface, while the amount of the magnetic field perpendicular to the plane will be 0, because it will be cancelled by the influence of the magnetic field due to the influence of the current, which is symmetric on the left-hand side and right-hand side. So in this direction, magnetic field will be 0. And in this direction, magnetic field will be constant in this along the line. And in this side as well, the magnetic field will be 0. So that if you evaluate this integration alongside the Ampere's rule, then you can say the magnetic field, strength of the magnetic field times length of the this rectangular. So will be, let's say if this is length will be L in this direction, and since the magnetic field in this direction is 0, you shouldn't count this part, so that the left-hand side can be evaluated in a way that the magnetic field times L plus, you should also take the line integration from here to here, which corresponds also same amount of the magnetic field with the length L, like this. So the left-hand side of this line integration will correspond to 2 times BL. And in this case, the right-hand side, you should have mu 0 and times the total amount of the current enclosed by the Ampere's rule should be evaluated, should be inserted on the right-hand side here, which will correspond to the kappa. Kappa is the surface current density, which will be a current when you multiply the length of the surface current density, so that like L times kappa will correspond to the total current in this case. Okay? So that if you equate left-hand side and right-hand side, you can find the B field in this case, which will be mu 0 times kappa divided by 2, and whose direction will be given in a y direction, let's say minus y direction, right? Minus y direction in the upper side of the plane, and with the same amount, you will have a y-directional magnetic field in the lower side of the infinite plane in this case. Okay, so in this way, by applying the Ampere's law, and you can find the strength of the magnetic field in a rather simpler way. And these are the simple example, because the current density in this case is distributed in a very symmetrical way. Okay, and this is how you can apply the Ampere's law to have the magnetic field in a symmetric, for the case of a symmetric current distribution. Okay. Right. And then we can also see the third example. This number is given 49 as solenoid. Solenoid, which is a specific case. I may write it clearer. Solenoid, which is the current distribution, which is winded in a column. That, let's say, if there is a certain column in a space, then if you're winding a current around it like this. Okay? And this is what we call the solenoid. Okay? And if it goes infinity, then you can say it's an infinite solenoid. And let's say there is a current flowing along the wire, which is winded in a column-shaped volume. Okay? Then the question we ask is what will be the magnetic field, either inside of solenoid or outside of solenoid in this case. Okay? So let's say this is an infinite solenoid, let's say, like this. And then we can find the magnetic field in this case using the Ampere's law too. So can be given if we take the magnetic field along the line, and it corresponds to the mu times total current enclosed by the line. In that case, the important thing is how we take the Ampere's loop. Okay? And the way we can take the Ampere's loop in this case will be symmetrical, that if you take the Ampere's loop going just above the solenoid and going just below the solenoid in this way, okay, then since the current is going inside of it, your thumb pointing to the direction of current, then you know the magnetic field around it will be in this case clockwise direction, which is pointing out by the toes of your fingers. Okay, and like this. Okay, and then if we see the cross section of the Ampere's loop in this case, so let's say Ampere's loop in this case is taken like this, in this direction, and in the plane of the Ampere's loop in this case, there is a solenoid wire which going through the plane and going inside of it. So there will be a current density located in this way, okay, and in this shape, right, and like this. And you will say, so let's redraw it. Okay, so for the case of solenoid, and if you see the cross section of the solenoid, then you will see at the tip of this cross section, the current will go in on the right hand side like this, and on the left hand side the current will come out, which can be denoted by this shape like this, as like the tip of the arrow. If you look at the arrow from the front, then you will see the point and then the round shape at the tip. And if you see the arrow from the tail, you will see the feathers in an X shape. So that in this side the current is coming out, in this side is current is coming in like this. And if we take the Ampere's loop, then it was in this shape, okay, going like this. And here also, we can check what will be the magnetic field either along this loop or and this loop. And what we can say about it is that we can equate this part of the current as kind of an infinite current plane, as like the case that we saw there. Then the magnetic field above this plane will be uniform, right? But uniform in a direction will be what? In the going up direction. going to this here. And the strength of the magnetic field will be uniform. Any position on the right-hand side due to this part of the current, and will be this. And if you look at the second part, and if you look at replace this wire current by the surface current that we have been seeing there, then also, like, since the direction of the current is going inside, and the magnetic field around it will be in the upper side, it will be going down, here, and this part, due to this current distribution, you will have a magnetic field going upper side like this. Okay? So that what you can say about the amount of the magnetic field in this part, you can say the magnetic field due to this current density, which is given denoted by the red line here, will be cancelled with the magnetic field due to this part, which I show here, draw here with the blue chalk here. And so they are cancelled because the directions are opposite and strengths are same. While the strength of the magnetic field inside will be non-trivial. In a way, the two magnetic fields due to this part and this part will be added inside. Okay, so that what you can say, and of course, so since the direction of a magnetic field are all the time going up, and magnetic field in this direction going orthogonal to it, will be 0. So magnetic field this part will be 0. Magnetic field this part will be 0. Magnetic field this part will be 0. And magnetic field and this part won't be 0. So that along this loop, the non-trivial magnetic field, what we can take is a magnetic field times, and let's say the height of this loop is L, then you can say it's just L like this. Okay? And this is magnetic field is 0 and 0 and 0, which will be the trivial. So this integration can be replaced by the B times L. And here again, so you should count total amount of the current going through the plane enclosed by the Ampere's loop in this case, can be given by the N times L times I, where let's say L is the winding number per length. Okay. Okay. For the case of this solenoid, you winding the wire around the column, then how dense the current that you wind it is depends on the how many winding do you have per length will be given, can be given by the winding number N. And so to have a total current, you should have a winding number per length times length will be the total number of wires, and the strength of the current in each wires will be given I, so that these correspond to the total current enclosed by this Ampere's loop in this case. Okay, so that if you and if you look at the equation here, and if you cancel the L both of the sides, and what you have the magnetic field inside of solenoid, and so that you can say the magnetic field inside of solenoid will be given mu 0 times winding number times I, which is the strength of the current going through the wire in this case, and which is the inside inside of the solenoid and will be 0. So magnetic field will be trivial outside of the solenoid. Okay? Solenoid. Okay? So that this solenoid is some kind of devices you can say is that the magnetic field inside of the winded wire is uniform and directly proportional to the amount of the current in this case. Okay? So this is the how you get the magnetic field for the case of the symmetric distribution of the charge densities. Okay? These are something you all know, and you have been seen in the general physics course, which I believe. Okay. And the next example, 5.10, is the kind of current distribution called the toroidal coil. Toroidal coil. Is that, let's say, if you have a finite length of the solenoid, and if you bend them and then stick their head and tail together and then make it round, then that's what we call the toroidal coil. Or, I mean, so it's, or instead of having a winding wire on the around the column, you can winding wire in a square-shaped column, and then if you bend it and then make it round, then it will be in a shape like the donuts. Okay, let's say if you have a donuts, rectangular shape of donuts. It doesn't really matter whether it's a rectangular shape or round shape of donuts, but I just took the rectangular shape of donuts like this. Okay, and then in this case the current is winded like this. Okay, by the wire, right? You will see like this. Like this, and this is what we call the toroidal coil. And the question we ask is what is the magnetic field inside of these donuts? Okay? Or pineapple. I don't know. Let's say this is donuts. Okay? So then the question can be answered. So it's answered by through the application of the Ampere's law in an integrated form, and taking taking an integration of the magnetic line integration of the magnetic field will be mu 0 times current enclosed loop. So that the most important thing to apply this formula is to take the right loop of the where the magnetic field is symmetrically distributed, in a way that if you look at this toroidal donut, like from the view above, then you can see that it has a round shape and it has a hole like this. Okay, and let's say the current is flowing this direction. Then you can say that in this case the current is coming out in this side, like this. Okay, and so on. And if we take the Ampere's loop around it, since for the case of a solenoid, we know the magnetic field is trivial outside of it, which will be the same for the case of a toroidal coil. and the magnetic field only exists inside of it, which is uniform for the case of the column. But if you bend it, the magnetic field will be bended and will be uniform around the group that we can take has a center at the center of the toroidal shape, center of the donut, so that you can say that you can take the Ampere's group in this way, whose radius is given by S, if you like. Okay? And for that, if you apply this one, and you can say the magnetic field will be uniform around this group, so that you can say the left-hand side will be magnetic field times, and the length of the peripheral of this circle will be 2 pi s, which, and the right-hand side, you have a mu 0, and total amount of a current in this case will be, let's say, one wire carries a current I. It will be correspond to the I, proportional to I, and let's say the total number of the winding is n. Then we can say just proportional to n. Okay, so n times I will correspond to the total amount of current which going flow out from this from the inside the blackboard and the outside the blackboard in this case, when you take the plane enclosed by the Ampere's group in this shape. Okay? For that, from this you can say the magnetic field will be now proportional to mu 0 divided by 2 pi and Ni divided by S in this case. Okay? So this will be the strength of the magnetic field. And strength of the magnetic field is uniformly changed from the inner circle to the outer circle, disproportional to the distance from the center in this shape like this. Okay? So this is the magnetic field inside of the toroidal coil. And of course, you can say, so this is the inside of, okay, so this is inside of, so inside the coil. Inside the coil. And you say it will be 0 at the outside of the coil. Okay, so and that's how we use the Ampere's law to have the strength of the magnetic field in a couple of different cases of a symmetrical distribution of a current in space. Okay. And there can be many more examples, but I stopped discuss about the application of the Ampere's law in this case. Okay, and go into the next section, 3.4, which is about the comparison between the is about the between the magnetostatistics and the sorry, it's not statistics, static dynamics. Okay, so statistics, okay, is something we'll discuss here. That if you recall, this is just something we recall that we have been seen before, was that so for the case of electric field, electrostatic field, and we know two equations in a differential form, is that divergence of electric field is correspond to the charge density inside the Gauss's surface divided by epsilon 0, and this is what we call the Gauss's law. Okay. And we also have a second equation of this, that curl of electric field was what? Curl of electric field was what? Was 0, right? And we don't have a specific name for this, but the consequence of this is that there can be some behind certain property to specify the electric field, because that the curl, if the curl is 0, then the curl of certain vector is 0, then that certain vector can be derived from the gradient of a given scalar function, so that the electric field in this case can be expressed by the gradient of given scalar function, in a way that electric field is become like this, which is because curl of any gradient scalar function is 0. Okay, these two equations expresses the how does the electric field distributed in a space, and here we have the extra property of the scalar function to derive the form of the electric field. Okay, so this is the electric potential. Okay, electric potential, and we are ready to have to discuss about this something in parallel within this shape of the equation for the case of the magnetic field, and for the case of magnetostatics. Static field. Okay, so we have two equations. One is the divergence of the magnetic field was what? This one is 0, and then curl of the magnetic field is what? Is it mu 0 times J in this case? Okay, so this is what we called Ampere's law. Okay, and the meaning of this is what? So is no magnetic monopole. Okay, so I mean, the meaning of this is simple if you think about the Gauss's law in a way that the Gauss's law is if there is a charge distribution Q, and then if you take a Gauss's surface and the electric field going across the surface and whose divergence of that electric field is proportional to the amount of the charge inside of that surface. Okay? And that is possible because for the case of the electric field, it can be generated when there is a point charge distribution and at a distance r. So you have an electric field like this. If you have a point charge like 1/4 pi epsilon 0 q divided by r squared like this. Okay. So which means you can for the case of an electric field or electric charges, it can all the time exist as like a monopole as it is. You don't really need like a minus charge together with the plus charge all the time. Okay, they can be paired at certain circumstances, but they never. Each poles can exist individually at an arbitrary situation. But for the case of the magnetic field, whenever you have a north pole, and you all the time has a south pole attached to it. So in a way that if you take a certain Gaussian surface, which tend to describe the magnetic field in this case, is all the time inside of it, all the time you have the paired pole, such that you never had the divergence has a valid number, and so it will be all the time 0, because for the case of the magnetic field, it's all the time paired pole exists for the case of the magnet. Okay, so it's a paired pole in this case, so that you can never separate them apart. So if you cut them half, what happened? The half of that half become north pole, and the rest half will become south pole. Okay, so for that's what the magnetic bar look like. Okay, so that's the meaning of the third equation for the magnetic field. Okay, and that's the meaning of it. And this is the Ampere's law. So if you take the Ampere's rule, and the curl of the magnetic field are proportional to the current density go across the plane. Okay? So here we have 4 equations, and 2 of them related with the electric field, and 2 of them are related with the magnetic field. Is called the Maxwell's equations. Okay, so now here we say these forces are 4 Maxwell's equations. And you can actually describe all the possible electromagnetic phenomena using these 4 equations together with the equation for the Coulomb force and Lorentz force. If we have a formula for the force Q E plus V cross product of B, okay, and together with these 4 equations, and you can describe you can find the electric field in a space and the magnetic field in a space whenever there is a charge distribution or current distribution. And once you have the field, have the expression of the field in the space, then you can have the force that a point charge exists in that, or certain charge distribution or certain current distribution in the space will be described with this, and then you can describe every nature relevant to the electric field and the magnetic field. Okay, and these 4 are the very fundamental equations. But the only thing I remember is I want to make a remark on this, is that these are the equation for the case of a static field, which means fields are not changed over the time, and the charges and current are not changed over the time. Okay, so this is a static case, but for the case of the but these are the complete expression of the electric field and magnetic field in for the case of static free space case. Okay, so if you go inside of the material, the expression of Maxwell's equation is slightly changed, and once you have the change of the charge and current over the time, then the formula will be modified, but that's the topic that you will come up in the next semester. Okay. But anyway, so once you have these four equations, you can describe the most of the phenomena related with the electric charge and the and currents. Okay. And those, okay, okay, so that's the thing, and but we still didn't really complete the Maxwell's equation yet, because for the case of electric field, since we have the call of electric field is 0, that we were able to define the electric potential, which is the a scalar function whose gradient is the electric field. And there can be a similar kind of concept like this for the magnetic field. But for the case of the magnetic field, the potential is not given by the scalar function, but it's given by certain vector function, because its call is nonetheless trivial. So you cannot have any object scalar function, any object in the form of a scalar function whose gradient drives the magnetic field, because this is nonetheless trivial. But there can be a certain property called the potential, vector potential, we say in that case, will drive the magnetic field. So next topic is magnetic vector potential. Okay, and we should start from its definition. Vector potential. Okay, so it's comparable with electric potential, but electric potential is a scalar functional. But this is for the case of magnetic field, it's a vector functional. So that is defined. So because in this case, the divergence of the magnetic field is all the time trivial, and you can define certain vector potential to drive the magnetic field in the form of a call of A like this. Okay? And the reason is that once you have this one, and call of certain vector will be all the time 0 when you take a divergence on it. Okay? Which we will see here, such that let's say if you take a divergence of a certain call to any arbitrary vector, okay, then so you know that so this is, if you take a call, then a divergence, then the first term will be round of round x in the x component, and x component of the call of a certain vector will be what? Round a z of round y minus round a y round z. Okay, so this is the x component of the call A, and the second term will be round y and round y, and the y component of a call A will be what? Round a x round, y, z, right? Z minus round a, z, round x, okay? Plus third will be round z, which correspond to the divergence, and the z component of the call of the vector A will be what? Will be round a y, round x minus round a x and round y, like this. And then, since the derivative operators are commutable as far as the function you have is the is analytical function, such that taking the derivative x and y with respect to the az will be comparable with az derivative x and y, and there is a minus sign which will be cancelled. Okay, so these two terms will be cancelled, and then so taking a z derivative with respect to x, ax, and take a derivative with respect to y will be also cancelled with the taking a derivative y and z, which is just the change of the order. So this and this will be cancelled, and you will see, and this part will be cancelled too. So that divergence of the call of a certain vector will be all the time 0, like this. Okay? And because of this fact that divergence of B equal to 0 means you can all the time define a certain vector potential whose call is given by a magnetic field like this. Okay? So this is a definition of the vector potential. But for the case of vector potential, there can be a more equation it should satisfy, which is the second one. Second Maxwell's equation for the case of a magnetic field, that once the vector potential is defined, it also should satisfy the Ampere's law. Okay? So that calls of magnetic field and here the vector potential, magnetic field expressed by the vector potential will be given in this way, call and vector potential like this. And so you have triple products of the vectors given with the gradients will be divergence of the gradient of A minus Laplacian to A, right? Which will correspond to the mu 0 J for the case of the Ampere's law. Okay? Oh no, the order of this is changed. It's a gradient times divergence, sorry. So you recall the vector analysis, then, so this is a vector, and so you should take a second derivative, a derivative twice to that vector, and there can be two different ways, and one is you first make a scalar functional and take a gradient, or take the Laplacian to the a given vector. And so that if you analyze this and then you ended up with this, and the vector potential A meant to satisfy this inequality equations. But the way that this equation satisfies, and the full solution of the vector field, vector potential in this case, is not uniquely given. So this is a kind of a differential equation. So the solution of the differential equation is highly depends upon the initial condition of it for the case of the dynamics. And as like that case, in this one as well, the vector potential is not uniquely determined, even if you have a current distribution in a space. So that the way that you can have the general set of the vector potential which satisfies this Ampere's law will be given by the certain mathematical trick called gauge transformation. So that different gauge transformed vector potential specify the same current density in a space. Space is the constant. So let's say there is a vector A, vector potential A in a space can be transformed to the another vector. Another vector potential without changing the shape of the magnetic field in the space, and which is in a shape from the original vector potential plus gauge term, which is a gradient of the certain scalar function, arbitrary scalar function. Okay. And so, which means, so change of which is so gauge transform is a description of change of the vector potential. Vector potential. While in the way to lift the magnetic field invariant. Okay. So magnetic field is not changed even if your vector potential changes with this amount. This amount, when I said that this amount is arbitrary, so like lambda is arbitrary scalar function and whose gradient is applied to it. Okay. So and the reason is that the why is it that so can be easily justified. Because curl of magnetic field in this case, let's say, and if you take the curl of the transformed vector potential, okay, so you can say okay, so for the case of magnetic field, which is coming out from the curl of the given vector potential, and if you transform the vector potential to the vector potential times gradient of a certain scalar function, then you will see that the curl of A will be like this, plus curl of gradient of certain scalar function will be like this, and then you can see this is a 0 all the time, and you have a curl of A. Okay? And you will see this is 0 all the time because gradient of lambda will be given. So col will be x, y, and z. And then component will be round x, round y, and round z. And the gradient of lambda in the x component will be round x and the lambda, round y and lambda, round z and lambda like this. And lambda, it can be a function of the x, y, z in this case. And if you look at each component, and let's say if you look at the x component, you will see taking a derivative of z and y minus taking a derivative y and z over the lambda will be all the time 0. So if you look at the x component, you will see round square of lambda of round y, round z, minus round square lambda, round z, and round y, and so on. And each term of the vector will be all the time 0, such that this will be all the time 0. Okay? So which means even if you take a vector potential with the extra term in this shape, then it doesn't really change the magnetic field in any case. Okay? So that in this case, the magnetic field is invariant. So that B is invariant to the transformation. This is what we call the gauge transformation. But then you can ask a question. What is a proper way to specify that gauge field? So vector field can be kind of arbitrary up to the gauge field. And then how we can specify the right vector potential and the right gauge field is kind of question we will ask here. And that can be given by the form of the equations that specify the vector field and the gauge field in this case. Okay? So, how many? Okay, we still have enough time. So by setting, let's say we start with the original vector potential is let's say this is insensitive to the divergence. Then let's say you can all the time take divergence of the original gauge field as 0. Then which means divergence of a vector field times gradient of certain scalar field like this. Okay, this must be in this shape. Is also times 0. Which means by setting criteria that you can all the time have divergence of vector field is something you can define the scalar function, gauge scalar, in the form of a Poisson equation. In a way, the first term, second term will be Poisson, the Laplacian of the scalar field, and the second term can be given as a minus of a divergence of vector field A. Okay? So that once you set or specify the vector potential in a specified position, then you can all the time find the gauge field by the transforming A prime to the A like this. Okay, so that's the way you can specify the gauge field in a space. Okay, so the way you can solve all this is through we have Poisson equation for the potential. The vector potential. Okay. In a way from there. So if we set this was 0, this was 0, so our equation of the Ampere's law will be reduced into the Poisson's equation. In a way, Laplacian applied to the vector potential is minus times nu 0j. Okay? Whose solution? Whose solution? Which is readily given. We know the solution of this equation. Right? The solution of this equation is, so vector potential at the position R will be given mu 0 divided by 4 pi, and take integration of the j at the prime coordinate, and the gamma square, and the gamma is r prime minus r square, and take the volume integration in this case. You know the solution of this is given like this. And look like some of you are puzzling. But if I just give you the form of the Poisson equation that we have for the case of the electric potential, you can see why it is the proper solution of the Poisson equation. If you recall, for the case of electric potential, that it is given by the solution of electric potential of rho 0 as a Laplace equation. Oh, sorry, there should be the minus sign in the front. Rho of epsilon 0 like this, and whose solution is the vector potential at the arbitrary position was 1 over 4 pi epsilon 0, taking integration of rho and r prime and the gamma square. No, not square actually. It is proportional to 1 over gamma actually. So it's a 1 over gamma like this, and take the volume integration like this. Okay? Which solution is given like this. This is what we know from the class a couple of weeks ago. Okay? And the equation we have now is the same form, except that rho and v is now replaced by a certain vector quantity whose solution is given like this in this case. Okay? And once you have a vector potential like this, then and the gauge field also can be specified, but I will discuss about it in the next class. Okay? So let's continue from this in the next class. Okay? Thank you for your attention. Any questions?